Okay, uh, let's start with the Huygens observers. And for that matter, I'm going to start with a motivating example. The example is of a second order system. There are two state equations here. First equation x1 dot equal to x2 and x2 dot is equal to a function of the state and input, and output is the state 1 x1. And suppose for this nonlinear system, we can design a state feedback controller, gamma of x, that stabilizes the origin of this system. So if this is the control which we have designed, we substitute this control value in U, and this is our closed loop system. Now suppose for this system, we also go ahead and design an observer. So the observer equation would be x1 hat as the estimated state, observed state, x1 hat dot equal to x2 hat. And as we do in the case of observer, we derive this equation with an error input. So error is between the actual output and the estimated output. The actual output is x1. The estimated output should be x1 hat. So this is the error between the actual system and the estimated system. And that would be multiplied by a gain h1. This gain we have to design. Okay, so let us just formulate first equation. First equation of the observer is x1 hat dot equal to x2 hat, as that appears in the actual state equation. And then uh, we add here the error term, which drives the uh, estimation error to 0. We'll see it in a short while. Similarly, for the second equation, we have h2 and driven by the same error. Remember that the observer is always driven by the same error. The gains are chosen for each equation, as is the case in the linear observer. So this is similar structure, only that we are keeping the nonlinear functions as they are. Okay. Now, here I'm using phi naught rather than phi. So the difference between phi and phi naught is that phi naught is that book value or datasheet value. This is nominal system. Okay. This is nominal system. This is actual system. Actual system may be subjected to errors, parametric variations. So there is some question of robustness coming in picture as well. And we'll see that how starting with the book value or the datasheet value or the nominal model, we would start designing of the observer with the nominal model, and we will see in the later stages how uh, this value in the observer would not matter much, even there are if there are some parametric variations, how the gains which are chosen here would ensure that the changes in parameters or any difference between phi and phi do not really matter much. So that would give us some robustness properties as well, which are going to be valid in all general cases. In specific cases, there may be some uh, uh, discrepancies there, but uh, we can always, uh, as a rule, uh, design via simulation first and then implement it once we have satisfactory results. Anyway, so phi naught is being uh, included as in the observer because this is what we are making. This is the actual system. Okay. Now we define the estimation error. X1 tilde is the difference between the estimated value and the actual value of x1. Similarly, x2 tilde is defined as the difference between the estimated value of x2 and the actual value. And if I just go ahead and detect a derivative of this equation and this equation, so since I have already x1 dot available, and x1 hat dot is the observer equation, first equation, x2 hat dot is the second equation. So we just substitute these values in here, in here, in here, in here, taking the dot. We end up with this set of equations here, where delta is the difference between phi and phi naught. Phi is the actual system, phi naught is the nominal value. Okay, if I move forward now, before going before going further, I just want to highlight a few things here. X1 tilde dot is the estimation error equation, right? So we see here that estimation error equation has minus h1 x1 tilde plus the driving term is x2 tilde, and x2 tilde, the equation, the state equation x2 tilde dot has x1 tilde coming in and the term which is the difference between the actual system and the nominal system. If this difference is zero, if we exactly know, or the system is exactly as it is, and we exactly know the phi and we can incorporate it here, or the system has not, for that matter, changed uh, uh, in terms of its parameters, then this will be zero. So there'll be nothing over here. And if we just make the matrix out of it, which I'm going to show you in the next slide, this will not appear over there. Let's just look at that system. That system is going to appear here. This is my A node uh, system, because if we just go ahead and make x1 hat, x1 tilde and x2 tilde as state variables, and make the state equation in terms of matrix over here, you will be ending up with x1 tilde dot x2 tilde dot in a vector equal to a matrix called A node. A node will have minus h1, then 1, and then minus h2 and 0 plus delta x tilde. So you are going to end up with this matrix. And our goal is now to make sure that we design h1 and h2 such that this matrix is Hurwitz. So this is again the same eigenvalue assignment problem. Now what we need to do is to ensure that the transfer function of this given system, now this is very important point to understand. This is my, these are two equations of my state system, okay? And the input is here, okay? This is my input. And this is my, turns out to be the error system, which I have to stabilize. My goal here is to make sure that x tilde goes to 0. If x tilde goes to 0, that means x1 x1 hat approaches the estimated value of x1 approaches to the actual value of x1. Similarly, estimated value of x2 approaches the actual value of x2. So if this is the driving term, I would rather want that the transfer function from this input to the state should be 0. So the transfer function from this input to the effect of this one should be 0. If that can happen, then x tilde will always go to 0, no matter if there is any, no matter what is the difference between these two. That means we are going to make the the uh, the difference between the actual system and the nominal system uh, not mattering at all. If that can happen, Then we are going to figure out the transfer function. Transfer function from delta to x tilde. If this is my state equation, and we know how we can find transfer function from this state equation. For example, if we just make an A matrix out of it, a B matrix out of it, which is here, and then a C matrix out of it, uh, that means my output would be x1 tilde. Then I can make I can find out a transfer function from the matrices A, B, and C. Okay, and that transfer function would be here. Now, if we bring in the transfer function from delta to x tilde, delta is my input, x tilde is my output. My transfer function is here. Now let's very carefully look over here. I want to make this transfer function to be 0 because I do not want that there should be any impact from input to output. Input in this case is the difference between the two things, the actual model and the nominal model. This is the parametric variation or perturbation. I do not want this one to be affecting my x1 tilde and x2 tilde. I want x1 tilde to be going to 0, x2 tilde going to be 0. By choice of h1 and h2, I should be able to do that. Now, what h1 and h2 will make it happen? So for that, I'm going to find out the transfer function from delta to x tilde, which appears to be here. What I'm going to see, what I'm going to see is an equation where I have h1 and h2 appearing. And now if I choose h1 and h2 appropriately, I can ensure that this transfer function remains 0 or as small as possible over the whole range of frequencies. Okay, if I choose h1 to be alpha 1 over epsilon, where epsilon is a very small number, and h2 to be alpha 2 or epsilon square. So alpha 1 over epsilon, that's h1. h2 is alpha 2 or epsilon square. If I had third equation, h3 equal to alpha 3 over epsilon cube. If I had the fourth equation, h4 equal to alpha 4 over epsilon power 4 and so on. So what happens? If I choose epsilon to be very small number like 0.01, so this will be 0.01. Alpha 1 is a number, an integer. 1 over 0.01, that means 10. 1 over 0.0001, that means maybe 1,000, and so on and so forth. If I choose h1 to be this way, h2 as this way, and I substitute h1 here and h2 here, and then do some substitution and do some manipulation, I will end up with the same equation written down in this manner. So I have now epsilon or epsilon s square whole square plus alpha 1 epsilon s plus alpha 2, and over here I have epsilon. Okay, this epsilon matters here. If this epsilon is very small, which we have chosen to be very small, that means this whole thing will be multiplied by a very small number. That means the transfer function from the disturbance or the variation between input, variation between the actual system and the nominal system to the estimation error would be negligible. If that can happen, then that means we have kind of made the influence of the difference between actual system and the nominal system immaterial. And despite this difference being there in reality, our estimation error goes to 0. That means the estimated state x1 approaches x1, estimated value of x2 approaches x2, while there is a difference of that system being uh, um, um, while there is a system difference between the actual system and nominal system present right there. By choice of these gains. Now this is the idea which Hassan Khalil introduced, and based on that, what happened? What happened that the transfer function between the transfer function from the the variation into the system to the estimation error became negligible, and that actually made this observer a robust observer, and it also gave us a very systematic way of assigning or finding the observer gains for the system, and that actually becomes very nice choice of observer gains, and we'll see in the example which is going to follow quickly in a couple of slides, that by choice of this systematic uh, observer gains, we can achieve a wonderful performance from this observer. And if we see here that when we are assigning the observer eigenvalues, uh, we get this set of this equation, and this equation actually renders the error from delta to x tilde of the order of the epsilon, and if epsilon is kept really small, the error estimation error is really uh, very small then. Now, in order to evaluate that mathematically, we define new variables. These are called scaled estimation error. I call these as estimation errors. These are estimation errors. The new variable which I'm defining here is called scaled estimation error. Why? Because this is the same estimation error as before, but this one is being scaled or being divided by the vary parameter epsilon, which is the design parameter for that matter. Okay, once we have designed these, once we have defined these, I just take the derivative of these, and with a manipulation, simple manipulation by substituting x1 tilde dot and x2 tilde dot, I end up with these two equations. Now, these equations, we have not covered that topic in our courses. Uh, this is a result from singular perturbation theory, because if epsilon goes to zero, we have singularity in these equations, and we do not end up with any solution for that matter. Without referring that theory for the sake of simplicity, we just have to see here that epsilon appearing here actually renders the effect of the disturbance, which is the difference between the actual system value and the nominal system value, to be negligible. And that makes sure that the ultimate bound on the scaled estimation error is order of epsilon. And the estimation error, scaled estimation errors, decay faster with this particular rate. The rate or the exponential mode is given here. So the estimation error actually approaches to zero faster, very faster, exponentially faster. So what happens that the estimated value of x1 approaches the actual value of x1, and estimated value of x2 approaches the x2 actual value of x2 exponentially uh, fast, and that is what makes this observer uh, very attractive. However, there's an issue called peaking phenomena. This peaking phenomena occurs if we have a huge difference between the initial conditions of two things. If the observer is initialized far away from the actual system, this error is going to be huge. If this error is going to be huge, remember that this H2 is 1 over epsilon square, alpha 2 over epsilon square. This is going to be huger now, more huge. If this is going to be more huge, this is already huge. What happens that the control, the effort is going to be huge in order to render the estimation error to be zero. So that actually may make something called peaking phenomena, which may render the system to approach uh, the finite escape time, now which is not a desirable phenomenon. So in order to avoid finite escape time, which actually makes the system unstable, we have to uh, uh, do some preventive measure. One preventive measure is to saturate the system in the beginning. Very small interval in the beginning, the system is saturated so that the the estimation error doesn't drive the system crazy or attain the finite escape time. So we'll look at the example and I'll show you how that is going to happen. Okay, this is one very simple example, and just look at the approach we are going to take while designing this powerful observer in a very systematic and simplistic manner. If these are the two equations of the system, second order system again, and output is having x1 in there. So if we have to design any controller which involves x1 and x2, we need to estimate x2 from the system. Okay, because output only contains x1, so we need to have x2 available. What we do, we actually go ahead and estimate both the states. Okay, that will also enable us not to use any sensor for measurement of output for that matter. We can just use the estimation for our control purposes. Now, for this system, assume that we are having uh, this controller over here. Now, this controller is interesting. Why? Because this controller actually is linearizing this whole system. So this controller is based on the idea of feedback linearization. If we apply u equal to minus x2 cube minus x1 minus x2, so this x2 cube is cancelled when we apply u here. So this is cancelled. So we have successfully cancelled the nonlinearity and included two linear values of the x1 and x2. So this whole system becomes linear. And now what we are going to do, we are going to make this state feedback controller to be an output feedback controller. What we need is, instead of x2, we need x2 hat. Instead of x1, x1 hat, x2, x2 hat. Okay. So observer is going to be this one here. Okay. So u is going to be all the hat values. Fine. All these hat values are coming from the observer, which is given by the last two equations. And now look at the observer. x2, x1 hat dot equation involves x2 hat as before, plus alpha 1 is 2 here over epsilon, and output minus the estimation value of x1 hat. Okay, so this is fairly simply the equation as we saw before over here. Okay, so h1 in our case is 2 over epsilon, alpha 1 over epsilon, alpha 1 is 2, epsilon is the design parameter which is kept very small. I'll show you. Okay, the second equation should have used x2 cube and then plus alpha 2 over epsilon square times the error. Okay, we are omitting this whole thing to get all together because we saw here that this thing shouldn't really matter. So we are going to skip it altogether. Why bother if it is not going to matter? We are just using h2 over y minus x1 hat. So this is my alpha 2 over epsilon square. These are two gains. Okay. So this is my observer. And when I implement this one, I actually get very nice results. And these results are shown here in these three plots, x1, x2, and u. In all these cases, the the solid line shows the performance of the state feedback control. Okay, no observer being used over there. But in all other three plots, in all these three plots, the three other lines which are dashed, dotted, dash dotted, corresponds to the output feedback controller with choice of epsilon values. One epsilon value is zero point 0.1, the other one is 0.01, and the last one is 0.005. I would like that you try to simulate the system, and by choosing these epsilon values, you should be able to get these plots. I have given you this homework problem as well for your practice. Okay, and you should be able. Now I'm going to show you the the effect of peaking phenomena. What happens in this particular example, if you go and choose epsilon equal to 0.004, the states actually uh, become unstable, and that's the plot here. Now, interestingly, uh, the initial conditions in this particular problem uh, render the choice of initial condition in this particular problem render this system to attain a finite escape time. So this is very interesting. We can avoid this by saturating the control. So instead of using a control like this, we just saturate it in the beginning, okay, by using this saturation function, and then we can go ahead and implement it, and things will be okay. Okay, so that is just to make sure that the system doesn't attain a peaking phenomena and doesn't go to a situation where you end up with a finite escape time and your system becomes unstable. Okay, under the state feedback, we are going to expect that our region of attraction will be bigger. Okay, so if in this case we are using this state feedback control, we will have a certain region of attraction. For example, in here we can see a plot between -3 and 3 and -2 and 2. This is the phase plot. Okay, now if I go and use the output feedback, it is expected that the region of attraction will shrink, and that region of attraction uh, will shrink based on the choice of the epsilon value. If epsilon is zero point 0.1, then we have the dashed. This is our region of attraction, so it is shrunk considerably. If it is 0.05, more. If we can reduce epsilon even further, 0.05, instead of 0.05 we can make it 0.01, probably we'll end up here. If we shrink it even further, we could reach to this kind of value, but more we bring it near to zero or more we reduce it, we may end up with the peaking phenomena again. Okay, so there is always a trade-off between these. To what extent you can bring epsilon smaller enough, that will be uh, that will be investigated using simulations. Okay, so just to summarize, what we need to do is to choose H1 and H2 and H3 and H4 depending on what order of the observer we are dealing with. Okay, and then we just go ahead and make observer equations following the example here and apply those observer gains. If we have two equations, then it will be alpha 1 or epsilon. Second equation will have alpha 2 or epsilon square. Third equation will be alpha 3 over epsilon cube. Fourth equation will be alpha 4 or epsilon power 4 and so on and so forth. Choose the value of epsilon. You can arbitrarily choose these alphas, alpha 1 equal to 2, alpha 2, anything which is a positive integer that will work, and you can check through simulation about the performance. Okay, can we use these for uh, a stabilization problem? Okay, let's see. Now I'm looking at a general problem which has the equation in a normal form, where a and b is in a controllable form, and if we have system in normal form, then we can conveniently apply this one. Just uh, make the observer exactly uh, based on the equations which are in the external subsystem, because in the normal form we'll have to really see whether the system is minimum phase. If the system is minimum phase, we'll just forget about the internal dynamics or the zero dynamics. We'll just check whether the zero dynamics is stable. If the system's zero dynamics is stable, then that system is called a minimum phase system. We'll just look at the other part of the equation, which will be like this, and we will make the, because this is the internal dynamics, this is the external dynamics part. We'll just make the observer based on this equation. Okay, and just to give you an example of a mechanical or electromechanical system, just look at the example of magnetic suspension system or magnetic levitation system. The system comprises of three equations. Okay, and we can use the um, if we have the system in normal form like we have in this case, the last equation has the control. The other equations are without control. We just go ahead and check the relative degree. Based on that one, we decide whether the system has internal dynamics or not. And if we have a system which has internal dynamics, uh, then we'll just go and check the zero dynamic of the system. If the zero dynamic of system are stable, then we are dealing with a minimum phase system. So we'll just forget about the internal dynamics, because we expect that if we design the control for the rest of the system, then that controller would also render the states of the internal system or zero dynamics to be stable in the meanwhile. Okay. Now, to make that discussion uh, uh, compact, let us consider that we design a partial state feedback controller for that kind of a system. Okay, and we will have to follow some steps. The first step would be to uh, bring in the closed loop system uh, into the bring in the closed loop system uh, under the state feedback. Okay, so we'll have to redefine the state variables and bring in the uh, uh, closed loop system while we apply the control, and we'll have to see whether the closed loop system under the state feedback control is asymptotically stable. Once we have the uh, closed loop system under state feedback shown as asymptotically stable, then we will, in the next step, design the observer by just following the equations as we have just seen in the example. Okay. The H matrix, which is appearing here in the observer, will have alpha 1 over epsilon, alpha 2 over epsilon square until we reach to the relative degree part. So we'll have exactly uh, that number of state equations equal to the relative degree, and accordingly we'll have the gains h1, h2, h3, h4 until h rho. So we'll have those kind of and these gains will satisfy this polynomial. Uh, I'm showing these equations which are actually discussed in the section 14.5 of the book. That's why I'm showing them here, because these equations or this formulation or problem statement has been used to show uh, the results which are given in theorem 14.6. I just want to uh, give you an idea using this example for that particular approach. Okay, this is example 14.19 in your book. Once I discuss this one, I'll go back to the theorem and I'll explain what that theorem actually means. Okay, this system is the pendulum equation, and the pendulum equation given here, uh, uh, there's a requirement that we want um, the pendulum angle to be stabilized at a value pi. Okay, and suppose we only measure theta. Theta is the variable x1 in our calculations. Okay, okay. So we want theta. We want that we only measure theta and estimate theta dot and apply that in our controller. Okay. So this problem has already been discussed in section 14.1 when we talked about sliding mode control a couple of weeks earlier. And in that particular lecture, we were able to come up with a controller which is given here. Now this is a sliding mode controller, okay, for stabilization of that pendulum equation. Okay, and this controller achieves the required stabilization at theta equal to pi. Okay, now if we want to implement this sliding mode controller using a high gain and using only measurement of theta, then we go ahead and design the observer which is given here. So this is x1 hat dot and this is x2 hat dot, because x1 is theta and x2 is the velocity, angular velocity omega. Okay, so this is my x2 plus alpha 1 or epsilon, and this is my theta minus theta hat, x1 minus x1 hat. And similarly, we have used here phi naught, um, and we have used the nominal values of that particular problem. So we could use or we could not use. You can omit this one and see if omitting this one or including this one gives you different results. Now, this corresponds to the discussion we had before. In this particular case, which we saw before, we did not use x2 cube over here. In this particular case, when we are dealing with example 14.19, you could try, use it or don't use it. That is up to you, and see what happens. You will find a very negligible difference in the performance. Okay. And now you have a couple of options here. Number one, you can use theta hat as well, and you can use theta hat dot as well. Okay. Like for example, this is theta hat and this is omega hat, because this is the angular velocity of the system. Okay. So from the state feedback control, you can go to the output feedback control by only using the second state over here or both of them. So these are two choices you have. You can use estimate here and estimate here, or you can use, because you are measuring theta anyway, you can use the actual measurement value and the estimate value. So this is up to your choices. This is your choice. If you use estimate here and estimate here, then you do not need measurement as well. But if you're measuring anyway, you can use the measured value that will give you probably more accurate values. But in all these cases, it is expected that your observer would give you a sufficiently uh, uh, close performance, uh, ultimately bounded performance by the bound epsilon. So epsilon is going to be your bound, ultimate bound of the convergence or stabilization. These are the results for this particular problem, and I would like you to actually redo this example. This is second part of your homework problem, which I've assigned you for this week, and I would like that you uh, come up with the same plots as are given in this particular picture. Okay, just to summarize the result, the theorem says that if the origin of the state feedback system, if the origin of the state feedback system under the state feedback controller is asymptotically stable and R is its region of attraction, then there exists an epsilon. That epsilon is actually this particular parameter we are talking about. Then there exists an epsilon so that the solutions of the new system with an observer starting in that region of attraction we are talking about will be uh, will be bounded. Okay, that means the the state feedback system, when subjected to a controller which is based on the estimation of the states using a Huygens observer, will still remain stable. Okay, this is what it means. Then this talks about that, for example, the states of the system, the original closed loop system under state feedback, are bounded by mu. Okay, and the estimated state is also bounded by mu. Then the difference between the the uh, the state feedback and the output feedback will remain bounded by mu. So all these results are actually showing that the Huygens observer is going to ensure that if you have a system and then you have designed a nice state feedback controller for it, which gives you required or desired boundedness properties, then the Huygens observer is going to preserve them in in true letter and spirit. Okay, if you choose the epsilon the right way. So that's what it is saying. Key ideas of this theorem. This is a wonderful theorem, and the proof of this theorem actually is spread over uh, about 6 or 7 pages. So you can have a look at the proof. But the key ideas of the proof are that you represent the closed loop system as a singularly perturbed system. Since we have not dealt with singularly perturbed system in detail, so um, I do not want to go into the details about that at this moment. Um, One idea is that you split the states into slow and fast. Okay, using the scaled estimation error we just defined earlier, and then use converse Lyapunov theorem to construct the required positively invariant set and show that all the trajectories under the state feedback and then output feedback converge to those sets, and then use the global boundedness approach to show that uh, the difference between the estimated value and the actual values actually goes to zero, while showing it that it approaches to a very small positively invariant set and reaches to zero in a finite time, or reaches to the value of close to epsilon, which is small enough or approaching to zero, in finite time. And this actually also shows that this particular observer is not really local. It actually has a, a region of attraction which is sufficient for the purpose of implementation. So it is not a local kind of thing. It is very much close to the actual system's uh, region of attraction. And by appropriate choice of epsilon, if we reduce the epsilon more and more and more, then we can actually make sure that the region of attraction of the output feedback control is similar or approaches to that under the state feedback control. And the novel feature of this whole proof or the theorem by Khalil was the performance recovery. It actually explicitly shows that the output feedback controller, which is given here, any of these actually recover the performance of the state feedback controller. Remember that the state feedback control, that means the states being fed in, actual states being fed in through measurement or through actual connections. You cannot have the better controller than the state feedback controller for no matter what. An output feedback controller can do what it can do is to go to that kind of performance, to reach, to approach the performance of a state feedback controller. And all this result is saying that an output feedback controller which involves a Huygens observer is going to make sure that the output feedback controller recovers the performance of the state feedback controller, which means the output feedback controller, which is being fed through an observer, will ensure that the performance of this controller, which is output feedback controller, reaches or approaches the performance of a state feedback controller. So if you design a nonlinear sliding mode robust controller as a state feedback and you employ a Huygens observer, you are ensuring that the performance of the sliding mode controller, which is robustness, is still achieved using an observer. So these are some powerful ideas or powerful results, and I would like that you experiment with them using simulation, and I hope you will be able to implement them, simulate them, and learn from them the different kind of variations which you can do by choosing the epsilons, by seeing that um, choice of epsilon actually is going to render the changes in the performance. So here is uh, uh, I've given you a homework problem based on these uh, two examples, and I would like that you uh, solve these examples. And the first problem in the homework is for you to uh, simulate this system and get these results, use this controller and achieve this particular uh, plot here, which is on slide 22. And then you also go and um, design the sliding mode controller for this problem, which you have already done. And then use a Huygens observer, implement any of these controllers, and obtain the results which are given on slide 35. This homework will be due um, next week, and I'd like that you all submit it in time, inshallah.